So we made this statement in passing, but I just wanted to show you kind of a quick little derivation that proves the point, because what we're going to do today is we're going to focus in on one type of motion and its contribution to, say, for example, the total energy. And we had just got done talking about the idea that, hey, if you want to look at something like internal energy, what you need is all motions. You need to look at big Q. And the formula that we saw for internal energy, right, was kT squared d the natural log of big Q dt, okay? So I made mention that, well, everything kind of separates out because of the mathematical form that we see of this expression. And now I'm going to kind of justify that a bit more. If we use our definition of big Q in terms of the small q's, okay? So I'm going to use 1 and 2 because I don't want to sort of take the time and the actual space to write trans or vibe or rote. So 1 and 2, that's going to stand for different types of motions. So what I did here is big Q is defined as small q raised to the n, small q raised to the n, all multiplying each other, and then divided by n factorial. All right. Now, if you look at the natural log, all right, term inside this partial derivative, we see that we can break it into a sum or difference. We can use the properties of natural logs to say, okay, if these are multiplied inside the natural log, then we can write it as a sum, all right, of natural log terms. If this is being divided by an n factorial inside the natural log, that looks like a minus natural log of n factorial term. Okay? I can then make this substitution back into our u expression, but then I realize that there's a partial derivative with respect to temperature here. And I have this natural log of n factorial term here. And even if I look at this partial derivative, it says that n is constant. This term is inside, okay, this derivative, so it really doesn't matter. It really goes away. And so what I'm left with then is a sum of two partial derivatives. One of the partial derivatives just has q1 stuff, and the other partial derivative just has q2 stuff. So all I did then was I took this and I substituted it in there. If this is all the q1 stuff, then it looks exactly like a normal expression we would have, except there's no n factorial term in the denominator, but we know that that's 0 anyway. So really it kind of fits our definition of u, except it's only considering one motion, okay? So this is going to be like translational contribution to the total internal energy. Same thing for this. Say if this was vibrations, okay? And our 2 stood for vibe, and we know what small q was for vibrations, and we'll be looking at that soon, right? This would be the vibrational contribution to the total energy then. Okay, remember another way of writing this would be like average E for motion 1 plus average E for motion 2. Okay, so we can use our big Q formulas in a way where everything separates out and you're actually just looking at the contributions for one component. Okay, so everything we talked about last time about translational motion will always have that kind of translational contribution to the total energy no matter what. Okay, so what we're going to do now is we're going to look at vibrations. And this will be the last type of motion that we get to talk about in detail. But again, remember, I should be able to throw like any small q at you, any big Q at you, and you should be able to execute the mathematics, take limits, analyze your results, make sense of your results. All the stuff we've been doing, right? It's just a mathematical process that you should be able to follow, all right? So let's look at vibrations. And it turns out, and again, I'm going to state this without actual proof, mathematical proof, because we don't have time, that Q vibe is equal to e to the minus beta h nu over 2 divided by 1 minus e to the minus beta h nu. Okay. Just to remind you some things, this is all excuse me. This is all based on the harmonic oscillator approximation, where we had energies that depended on the quantum number v, that made a ladder, v plus 1/2 h nu. So this nu that's up here is the frequency of our vibration. H is Planck's constant, right? Again, there's work happening in the background here, right, that lead us to this sort of expression. Okay. So now what we're going to do is we're going to analyze this Q like we analyze other Qs, like when we did a 2-level system, etc. And we're going to start to justify some of the statements we've been making about most things being in the ground vibrational state at room temperature, all right? Let's take a look at P0 though first, all right? P0. So if I look at P0, all right, the probability to be in the ground state, okay, so now this 0 is actually referencing like a V equal to 0, the quantum number itself here, okay? We know that that is e to the minus E0 over KT, right, divided by our Q. So we use our definition of population from earlier. Now we're specifically talking about vibrations. This E0 means something because we actually know what the functional form is for the energy levels of our harmonic oscillator. So what we do, just to show you again, right, is we go 0 plus 1/2 h bar omega is the energy of that ground state. So we make the substitutions, and what we get is, okay, so Q's in the denominator here. This fraction here, this whole entire fraction is Q. So instead of dividing by Q, I'm going to take this, I mean, I'm still going to divide by Q, but I'm going to invert this fraction and multiply. I'm also going to make this substitution. This looks like 1/2 h bar nu. Sorry, 1/2 h nu. There's no h bar here. 1/2 h nu is E0. Okay. So then this is going to look like e to the minus h nu over 2. The denominator here gets flipped to the numerator, e to the minus beta h nu. And then this stays in the denominator, e to the minus beta h nu over 2. So this looks like my, right, P0. Ooh, sorry, h nu over 2, and there's a KT here. So this looks like my, all right, P0, but we can simplify further. And we remind ourselves that sometimes we write the KT and sometimes we write beta. And whenever you see a beta, right, it translates into a 1 over KT. So if I look here and I look here, either think about taking this beta and writing 1 over KT, or can you find a 1 over KT there that you can rewrite as a beta? This and this are actually the same. One's on the top of a fraction, the other's on the bottom of a fraction. So P0 is simply 1 minus e to the minus beta h nu. That's the probability to be in the ground state, right, under a harmonic oscillator approximation, right, for vibrational energy levels. Okay. You should be able to follow a similar analysis and be able to show, because I could ask you about any of these states, but you kind of saw how to do it for the ground state. What changes if we do something like P1? Right? Well, the quantum number changed, and that's it. So when I look for the population to be in that V equals 1 state, I still need e to the minus E1 now over KT, but I still have the same Q down here because I'm still dealing with vibrations. Now E1 looks like 1 plus 1/2 h nu, right? So it looks like 3/2 h nu. So I can plug this in here. I know what Q vibe looks like. Fill in the gaps, but you should be able to show that P1 looks like 1 minus e to the minus beta h nu times e to the minus h nu over KT. And be able to do this for any V, right? For any V. So now this is a formula that's valid for any temperature that describes the population to be in the ground vibrational state and the population to be in the first vibrational state. Okay? So let's take some limits and let's kind of look at what happens here. Okay? The easiest limit is a low T limit. Now remember, low T means something different for every situation. Low T is, okay, how does it actually relate to H and nu and K? How does it really relate to all this energy stuff that's there? So if we look at doing low T, we kind of know what the answer should be, but now we're going to see mathematically whether we can prove it. All right. So we're looking at low T now, right? So we find where T is in our expression. Well, T's in the denominator up in this exponent, right? So I have an h nu over kt there, h nu over kt there, h nu over kt there, okay? So h nu over kt, if I make t small, right, this term gets big. T's in the denominator, okay? So h nu over kt gets big. Now, E, okay, has this h nu over kt as a negative exponent. So if this exponent, this whole entire thing gets big and it's a decay, based off of arguments we made before, what it looks like here is we are getting, all right, well, this is big, it's a decay. Oh, it looks like this is going to 0. And then in this low t limit, all right, low t limit, we're going to get a 0 on the outside here. It doesn't matter what happens inside the parentheses. We get a p1 that's approaching 0. Here we're going to get a 1 minus 0. There's nothing on the outside, so we're going to get an approach of 1. So this proves what we were saying before, that for low temperature situations, and it turns out that room temperature in terms of vibrations is a low enough T where most things are in their ground vibrational state. Most molecules are vibrating in that ground state. Okay, well, let's actually make this, I like to take limits, so I just wanted to show you one more example. Let's actually do it though. Let's do an actual analysis for a specific vibration. Let's put some actual numbers in here instead of taking limits. And let's look at like 300 Kelvin, okay? And then let's take a look at actually getting numbers for these different populations, and you kind of see what I mean here, okay? Before we do that, I just want to talk about a relabeling that occurs. So we get really lazy in terms of how we write things. And so what we do is we define something called theta vibe, and this is going to be referred to as the vibrational temperature. Okay, and essentially all it is a grouping of constants. So inside each one of those expressions that we were just analyzing, what you saw is a lot of h nu over k. Now it turns out if h nu is energy and k has units of joules per Kelvin, this ends up getting units of Kelvin. So we kind of call this grouping of constants theta vibe. Now theta vibe, right, is an intrinsic property associated with this nu, associated with this frequency. So we'll say that each particular vibrational frequency has a certain vibrational temperature. But all it really does is it doesn't change anything about the mathematics. It's just grouping things up in terms of theta vibe. But you'll see tables in your book, and I'll give you information based off of theta vibe because that's normally how we report it. Okay? And then just kind of realize that what's happening here is there's different nus. So there's going to be different theta vibes that result. Okay? So if I take a look at like P0, for instance, okay? P0 was 1 minus E to the minus H nu over KT, right? H nu over KT. So another way to write this in a lazy way, but actually kind of helps, is 1 minus E to the theta vibe over T. Okay, so it's just, it doesn't change anything about our analysis. It's just what it looks like in terms of how we combine information and then also how we record information. And you'll see that with this example. Okay, so we're going to look at carbon monoxide, and there's one bond there, and it's a triple bond. It's a pretty strong bond. And actually we see that based off of its nu, we can calculate a theta vibe, right? So if I look at the frequency of the triple bond vibration there, I use the harmonic oscillator approximation, we get a theta vibe that is 3103 Kelvin. Okay, 3103 Kelvin. So now what we want to ask ourselves, okay, are questions like, okay, let's say we're at somewhere near room temperature, like 300 Kelvin, right? What is P0? And we can also calculate like P outside of 0. And you'll see what I mean in a second, okay, when we actually do this. because it kind of ends up being like an intrinsic part of the mathematics. So we want to know, all right, now here's something just direct with numbers at room temperature or near room temperature with a specific vibration that's been analyzed. What's the population for this molecule to be in the ground state? What's the probability? What's the population? Remember, those are synonymous. P0, right, looks like 1 minus E to the theta vibe over T. So it looks like 1 minus E to the, oh, sorry, and there's a negative up here. Make sure on that last thing that I had here, I can't remember if I included that negative. Don't lose that negative. It's very important, all right? This is definitely the correct P0, right, with that negative there. 1 minus E to the minus 3103 Kelvin divided by 300 Kelvin. So you see, say theta vibes given to us. We just plug it in there. They already kind of did math. It's nice. They did the H nu over K for us, okay? Kelvin and Kelvin cancel. That's good for an exponential, right? What I get is 1 minus 3.22067 times 10 to the minus 5. Now, right, this is the probability to be, okay, in the ground state. And we can come up with a number, and I'm just going to write it above here. So, right, when we do this math, what we get from a numerical standpoint is 0.99967779 as our probability to be in the ground state, okay? So if you want to think about it as a percentage, okay? Oh, there's another 9 here. There's actually 4 9s when I do it, sorry. 4 9s, let me just rewrite that. Okay? There's actually 4 9s here, so if you want to think about it as a percentage, it's 99.99% likely to find a molecule, okay, in the ground state. Now remember, all these probabilities, what do they have to sum to? They have to sum to 1. So I mentioned this whole question here at the top. What's the probability to be outside of that ground state, outside of that 0 state? Well, if the probabilities have to sum to 1, okay, then, oh, I have a 1 minus this here in terms of my P0. So whatever number you see here, this answers that question, okay? So if 1 is the total probability when you look at all molecules, and I have an expression for the ground state that's 1 minus some number, then this must be the probability to be in P1, P2, P3, all of those, okay? Now this is most likely going to be really close to P1, okay? Because if this much is in the ground state, there's very little that's going to creep up our ladder. Remember, temperature allows us to creep up the ladder, okay, of energy levels. So this is probably close to P1, actually, and it will be interesting for you to try to do that and actually confirm it, right, based off of this theta vibe and this temperature. But we see we can answer the question directly, okay, here's P0, right? Anything left over away from 1 is the population that's out of P0. So when we draw our little diagram and we think about molecules, right? I mean, 99.99% of the molecules are here. And if we would draw like a bunch of little X's here, there'd be like a small X that creeps up to the top there. Most molecules are in their vibrational ground state. Okay, so let's actually use these populations. Let's use these probabilities. So let's say now we continue our example and we have 1 mole of molecules. All right. Now we know that 1 mole is 6.022 times 10 to the 23rd molecules. So that's how many carbon monoxides we have, right? Let's get a number, all right? How many, not what percentage, not what's the population, okay, what's the probability, but how many of this many molecules, right, are in, all right, the V equals 0 state. So if you think about how populations work or how probability works, okay, if I want to talk about, all right, the number in the V equals 0 state, then what I'm going to have to do is I'm going to have to take my total and multiply it by the probability, okay? So if I have a total of 1 mole, and I think about what this probability means, right? Probability is always part over the whole. How much of this is a fraction, right? What fractional part of the whole ends up in that 0 state, okay? So we can just do that math here. We can put 6.022 times 10 to the 23rd there. We can use P0, right, as a multiplicative factor that tells us how many of those molecules are actually there. And what we get out is 6.02186 times 10 to the 23rd molecules. And I'm not really paying attention to significant figures. I'm just kind of showing you, all right, what the changes are. Now, how does this compare to that? I mean, it's almost exactly the same. And if you were paying attention to significant figures, it would kind of round to the same spot. And that's why I didn't want to do it. I wanted to show you that there are some molecules that creep away. Okay? But, I mean, the super majority, I mean, 99.99% of the molecules are in that ground vibrational state. What about the number of molecules that are outside of that ground vibrational state? So the number with a V greater than 0, right? How many climb up that ladder? Well, we could use this value, remember from the last part of the example, which told us how many are outside that ladder. We can multiply this by N, and I'm just going to call this like a general PV, right? And V is going to represent, okay, these V's that are greater than 0. If I use the number here that we used above, 6.022 times 10 to the 23rd, and I use this number here, right? This is going to be the total number inside that mole that start to creep up that ladder. Now, this number is going to look big, okay? But it's not going to look big compared to this number, and you'll see what I mean. So when I do this math, I get 1.9395 times 10 to the 19th molecules. So you might look at this, and we have to be wary of doing these sorts of comparisons. You might look at this and say, holy crap, that's 10 to the 19th molecules. That's a ton of molecules. But if you are going to try to pick out a random molecule in this mole, all right, and you're going to look at it and say, what V does it have? What is its actual quantum number? Okay? You are like 10 to the 5th more likely to find, all right, something in the ground vibrational state than something not in the ground vibrational state. Okay? So you have like a 10 to the 5th difference here, all right? That just makes it almost statistically really improbable, not almost improbable, makes it statistically improbable, all right, to find a molecule outside of the ground state. So here's a situation where we could even use like our two-level system analysis to approach this problem. Because as I mentioned before, most of these are probably in the V equals 1, all right? Very few are going to be in the V equals 2. It really looks like there's only 2 levels available, and in fact, at this temperature, 300 Kelvin, even though there's 2 levels available, it looks like, I mean, an incredible number of the particles are still inside that ground state, okay? We can take this analysis, and we can look at E-vibe. And remember, we justified it at the beginning of this video. If I want to talk about internal energy contributions from vibrations, and remember that looks like E-vibe, okay, then what I can do is I can take K T squared partial natural log, and I'm gonna even write in the n factorial there, because remember, it ends up like just not mattering at all, but just to show you that it follows the form that we set up before, right? So d natural log of q vibe to the n over n factorial, right? Partial that natural log, partial t, done at a constant n and v. So based off of, like I said before, the arguments we were making at the beginning of the video, this would be a way we could calculate, right, the contributions to the energy. Now, what we have is a q vibe from our last couple examples that we now could throw in there, okay? So make sure you can do this math. Okay. What we get for u vibe is n k theta vibe over 2 plus theta vibe over e to the theta vibe over t minus 1, okay? So we kind of get something that's a lot more complicated, and that's why I wanted to show you this. For u trans, we got 3 halves nkt, a nice simple form, okay? You might be asking yourself, where's t, right? T is here, right? T is here in terms of actual, T is here in terms of actual changes in this value based off of temperature. But also remember that these thetas are temperatures themselves, right? So this is the contribution to the total energy, total internal energy, based off of vibrations, okay? This is 18.25 from your book, and it kind of shows you, walks you through the math. But again, now that we've gone over this, and now that you see these partition functions just as these mathematical objects where we can get some important information from, okay? You should be able to go ahead and fill in the gaps yourself. You should be able to put Q vibe there and crank out this, right, expression for the vibrational contribution. We could ask ourselves, what's the contribution to CV, all right, from vibrations, right? Just make a little subscript vibe here. What's the contribution from to CV for vibrations? Partial U, partial T, done at a constant V. Could make it molar if we wanted to. Well, hold on a second, okay? Do I have an expression for U or U bar if I wanted to? Yeah, now I do. So I can even get a CV vibe here if I plug in a temperature derivative and then analyze from there. Now remember, this is a partial with T, so this is actually going to affect this right here the most. But again, it's all math from there, and it's all math that you know how to do and how to enact. Okay, so this kind of ends it for statistical mechanics. I know it's a lot to really get straight in your head, but do your best, okay? I've kind of alluded to the different things I'm definitely going to look for. Make sure you can work with a 2-level system. Make sure you know how to work with our translational partition functions and our vibrational partition functions. And just be ready if I throw a different partition function at you, like the rotational partition function, etc. Be able to throw them into these mathematical equations, do the work, analyze the results, talk about limits, talk about populations or probabilities, talk about total numbers now, based off the last example that we did, and really have a better idea and a better physical understanding of when you look at something at room temperature, when you're looking at an actual sample of gas or solid or whatever, you actually kind of think about these energy levels that are inside it and which ones are thermally available. That's what StatMech is all about, right? What levels are thermally available and how that manifests as observables like energy and heat capacity, okay?